Hello, my name is Tao San. I'm a second year master student in Snow School of Management. Today I'm going to present my final project on obstacle-free motion planning of KUKA robotic arms. The robotic motion planning problem has been interesting over the last decades as robots started becoming an important part of modern industry as well as in human life. Even though modern robots may possess significant differences in sensing and actuation and applications, etc., the problem of navigation through a complex environment is essentially in almost all robotics applications. Efficient automation with KUKA robotics ensures that the enormous demand for new electronics products can be met quickly. So robotic automation solutions enables extremely precise production with high repeatability, and small robotic solutions are integrated internationally into the assembly process. KUKA small robotic arms demonstrate one of their greatest strengths in extreme speeds, flexibility, and power. This produces impressive results with minimal cycle times. With high reliability and accuracy as required, KUKA small products are in their elements that enable manufacturing quality at the highest level. Due to their robust design, they work with continuous precision throughout the work envelope. The standard robots are ideally suited for installation in the floor, ceiling, wall, and angle to allow optimization utilizing in any mounting positions. So in this work, actually, I'm taking the KUKA robotics challenge design, which is organized as an open game by Crusoe Institute of Technology in Germany. So the purpose of this project is to implement path planning algorithms by navigating a maze. Usually, path planning problems through the maze are reduced to 2 dimensions. However, in this challenge, the project can be extended to search a place in the third dimension and the orientation of the grip around the vertical z-axis. So the experiment really is set up as follows. First, the robot will move to a start position, which will be the entrance to the maze. Then the gripper will pick up the object that is shaped like a cuboid, as you can see, as a green brick. Then the users take over and navigates the robots through the maze. The user will have to command the 2D position and the rotation angle in order to get around the corners and rotate it over the obstacles. Once the goal is achieved, the cubic will be placed in the table at the goal positions. The experiments will be successful if the user is able to get close enough to the goal position, which is a red brick in this plot, such as if the distance to the goal is smaller or equal to the discretization level. What I implement as a path planning solution is using the rapidly exploring random tree star algorithms. So RRT is an optimization version of RT star is an optimization version of the RT, which was taught in the class. It addressed the cubic nature and the irregular passes. When the number of nodes approaches to infinity, the RT star algorithm will deliver the shortest possible path to the goal. So as you can see in the algorithm, which is written here, the principle of the RT star is the same as RT, but there are 2 key additions to the algorithm resulting in significantly different results. First, the RT star records the distance in each vertex has traveled relative to its parent vertex. This is referred as the cost of vertex, after the closest node is found in the graph, a neighborhood of vertices in the fixed radius from the new node is examined. If a node with a cheaper cost than the proximal node is found, the cheaper node replaces the proximal node. The cubic structure of RT is eliminated. Then the second difference in RT star as is in the row Y in the tree. After the vertex has been connected to the cheapest neighbor are again examined. Neighbors are checked if they have been rewired to the newly added vertex will make their cost decrease. If the cost does not indeed decrease, the neighbor is rewired to the newly added vertex. This feature makes the path more smooth, and RT star actually creates incredibly straight paths. For finding an optimal path, especially in the dense field of obstacles, the structure of RT star is very useful. So here is the results of the motion planning. So you can see the robotic arms are going through different key points, which is found by RT star algorithms. And it starts from 1 and goes to the final steps to 8, and where the robotic arms can move the bricks from their starting point to the ending point. And next is the video to show the whole process. So to conclude, in this project, I demonstrated a solution for obstacle-free motion control in a 3D environment for KUKA robotic arm. RT star was used to determine the shortest obstacle-free trajectory from the starting point to destinations. In the future, I think in case of the robotic arm movements, obstacle avoidance in a dynamic environment is not more complex than in the case of a static point objects that, as I presented here. This is because in the current situation, we must not only make sure that any effectors, for example, the gripper avoids the collision, but also ensures that all its orientations, all the parts of the arm should avoid the collisions within the obstacles. So I think further analysis can be done in the applicability of the other popular evolutionary algorithms in the path planning of the robotics arm for energy optimization in a dynamic environment and study their relative performance. Thank you.